Alright, so in this video, I want to cover information about fractures and cracks and defects like that and how can they propagate in a material. Some important formulations to remember, which will be provided to you in the equation sheet, but you need to understand what do they mean and where to use them. And that's what we'll be covering right now. And then using some example problems to understand how to use these formulas to actually solve questions. So, some important numbers, you have sigma m, you have k subscript t, you have sigma c, you have k subscript 1c, where 1 is the Roman numeral. The sigma m is equal to 2 times sigma naught into a over rho t whole to the power half. The kt is equal to sigma m over sigma naught, which will be simply 2 times rho a over rho subscript t to the power half. Sigma c is equal to 2e gamma s divided by pi a to the power half, and then the k1c is equal to y sigma c root of pi a. Right, so let's see what these are. The sigma m is the maximum stress at the tip of a crack. What this is referred to. So let's take an example where imagine you have a sample of this sort, and it's sort of infinite or semi-infinite sample and extending in both lengths. Now consider that you have a crack, elliptical crack. So consider this to be an elliptical crack of so, and then we will say that the total length is 2a. So here the total length is equal to 2a, therefore the half length would be a. And in this system, at the ellipse, at the end of the ellipse, which would look like this radius will be given as rho of t, or also radius of curvature. So these are some notations that we need to understand. And you're pulling apart this material with a stress of sigma naught. So this means that at this material, what is happening here is that if you draw a plot of, let's say, the length, you'll notice that you were pulling with a stress of sigma naught, but at the tip of the crack, there is a higher amount of stress present. And so this length, let's call this minus a to plus a. So this would be 2a. And then this value over here would be sigma m, which means that at this tip, you have a higher stress than what you were actually applying. So you have to design your material according to sigma m, considering that you don't apply stress as high as sigma m. So therefore that is the maximum stress at the tip of the crack. Now the kt here is referred as the stress concentration factor, meaning that out of the stress that you applied, how much is concentrated at the maximum point. Therefore, it's the ratio of the maximum stress versus the stress you applied, so sigma naught. So it comes down to be 2 times the square root of a over rho subscript t, where a again is the half length and then rho is the radius of curvature. Now sigma c over here corresponds to the critical stress required for crack propagation. Meaning that only when, so let's write that on this side. So I'll write it here. Only when your sigma m is greater than sigma c, a crack will propagate. Meaning that this crack will move and propagate through the material only when your sigma m is greater than sigma c. So this becomes a critical and important condition when designing materials so that they don't fail. So we will design a material in a way that the sigma m remains less than the sigma c so that it does not fail, so that the crack does not propagate. Here the gamma, let's write that on this side. The E over there refers to the Young's modulus, and the gamma S refers to the specific surface energy, right? And then further you have the last term K1C, which you can refer as the plane strain fracture toughness. Now when you have fracture, so let's use another section, maybe on this side. So when you have a fracture, that can happen in three different modes. So fracture modes. So you have mode, and they're written in numeral Roman numerals. So mode 1, mode 2, and then mode 3. So with this type of system, what you have is that in mode 1 you will have a tensile fracture, or tensile or opening, and then in mode 2 you will have a sliding fracture, while as in mode 3 you will have a tearing fracture. Generally in materials, what you will see or what you will find is the mode 1, therefore that's what we'll study. And this fracture toughness that we are writing is for the mode 1, and therefore it has that Roman numeral 1 on it. And these are some important definitions. The y over here is sort of a let's call it a proportionality factor for now. And then it can vary depending on the geometry of your defect, or the crack, and then the geometry of your material. How does crack compare to your actual material? So what happens is that we took this example on this side. Let's compare that with another system. So I'll draw both of the systems. You have this example, and then let's draw another one. Right, so you imagine these two conditions. In the left hand side, let's say my elliptical crack is in the material, in the middle of the material, deep situated inside the material. While as let's say that on the right hand side, your defect or your crack is on the edge, or rather I should say the surface of your material. All right, so two very important things to note. For the left hand, so I'll also write this down as here. So this is inside, so crack inside material, and then crack on the surface. This crack could also be like a scratch. And if you read the book and other resources, you'll understand better what does inside and surface mean. It basically compares to the A versus the length of the material. But I'm just giving a brief of how you can understand this as two different systems. So again, let's say you are applying a sigma naught to both these systems. That is the applied stress. Let's write that down. Applied stress. Now, two difference between these two examples. The y value for the left hand side is given as 1, while the y value for the right hand side is given as 1.1. And here, when someone tells you that this, I have, let's say, the length of crack that is equal to 2a. So let's say I have a crack inside a material of length 1 millimeter. What I'm referring to is that 1 millimeter is equal to 2a in the system. But on the other side, when someone says length of crack, they are referring to the a value. So in this system, this length is considered 2a, which is the length of crack, whereas in this system, this length is considered a. So for the right hand side, if someone says that I have a crack on the surface of length 1 millimeter, then I'm saying that a equals to 1 millimeter. So please note these two difference in these two locations of crack. And when you try to put the values of a or y, a, you have to be careful accordingly, and for the y as well, both a and y, right? So let's try to look at some problems. These are problems taken from the practice exam, so I'll recommend you solve them first, then come back and try to understand now how to solve these questions, right? So let's do that. So this question number 6 is asking us what has a higher stress concentrator factor, a surface crack of 1 millimeter or an internal crack of 1 millimeter. So let's write down first, try to understand what is it the question asking. It's asking about the stress concentrator. So when you look at the equation sheet, you can look at the formula K subscript T, which is equal to sigma m over sigma naught, is nothing but 2 times a over rho t square root. This is again the stress concentration factor. Now let's write two different cases, right? So you have case 1 where it's a surface crack, and then case 2 where you have an internal crack. We know that, and also given the question, for surface crack y equals to 1.1, for an internal crack y equals to 1, and similarly the 1 millimeter, that is length, for a surface crack that will be a, but for an internal crack that will be equal to 2a. So when you find, or when you try to calculate, I'll write this down here, and I'm gonna erase this to get some, or let's not erase this, I'm just gonna move this to get some more space. So so when you try to solve this question, for k t surface, for, so this is a surface crack, right? And then this will be kt internal. Considering that rho t is constant for both the cases, which is the radius of curvature of the crack, this will be what, a over rho of t square root, which will be 1 over rho of t square root. While as for the internal crack, it will still be a over rho t over 1 root 2 or over root 2 of a square root, and then that will come down here. A will become 1 over 2, because if 1 millimeter is two-way, then A will be half millimeter. So this will look something like this. And this is how you can see which one is larger and which one is smaller. So this has a factor of 1 over square root 2. Alright, so you will see that this is how you can understand two different cracks, their different y values, their different lengths, and then correspondingly how to calculate their stress concentration factor. So again, this is the formula that we used, and therefore it is important that you understand what these formulas refer to and how to use them in questions. Let's do another question. So okay, this might be from a different section, but let's just still solve it. You have been given that a 1 millimeter cross 1 millimeter brass sheet is rolled to this dimension. Then what is the expected yield strength is cold roll to? So we can find the cold work percentage from the formula given to us. That'll be what, 1 into 1.2 the area. So I'll write the formula for you guys first. So that'll be area final minus area initial by area initial into 100%, right? So this will be 1 into 1.2 minus 1 into 1 divided by 1 into 1 into 100%. So that will be basically 1.21 is 1.2, so that will be 20% cold work. So if you look on the graph and then try to draw the line, so percent cold work is the x-axis. Look at the 20%. It's given that this is the brass sample. So let's go here and then let's draw this horizontal line. So it's approximately 50 psi or 320 megapascals. So the yield strength would be, let's say, approximately 320 megapascals. Alright, and this is how you can use the cold work formula. And then for the next question, name and describe the 3 steps within the heat treatment after cold working to make the material more ductile or fracture resistant. So the 3 steps that come here are recovery, followed by recrystallization, followed by grain growth. So the idea being in that in recovery, in the recovery process, you remove residual stresses and obtain defect free grains. Residual stresses or strains, you could call it. So you remove the residual strains in the material or the stresses, and then you obtain defect free grains. And then new grains nucleate in the recrystallization process, and then tiny grains which are defect free in the microstructure, and then you have a growth of grain. Also to answer, I just realized this previous question I did on the part, ductility increase or decrease. So what happens is that when you do the cold work, you end up adding dislocations. You add dislocations to your material. The more the dislocations, the more the hindrance for the material to elongate. So lesser the ductility. So the ductility decreases because of that cold rolling. Right, so Okay, let's solve this question. This will be related to the fracture equation that we just studied. Alright, so a 1 centimeter diameter aircraft is fabricated from aluminum alloy that has a tensile strength of 300 megapascals and a plane strain fracture toughness of 40 megapascals per meter square root. If a 0.5 millimeter deep surface crack or scratches might be present, what is the maximum tensile force that can be placed on the rod? Will the part fail by fracture or necking? So let's write down what all stuff do we know. It is given that the initial diameter is 1 centimeter. The tensile strength of the material is 300 megapascals. The plane strain fracture toughness, so let's consider this to be a mode 1. So K1C is equal to 40 megapascal meter square root. Now here it says it's a surface crack, right? So surface crack length is given as 0.5 millimeter. And again, we remember for a surface crack, the crack length corresponds to A. And then again for a surface crack, we know that the Y value is 1.1. And yeah, this is the information that is given to us. We need to calculate the maximum tensile force that can be put on this rod. So to calculate the force, let's calculate the stress it can sustain. So we know that the critical stress is in the formula of K1C. So the K1C is given as Y times critical stress square root pi A. So we can get the value of critical stress from here. So that will be 40. Be mindful of the units, by the way, guys. Meter square root equals to 300 megapascal multiplied by sigma c. Oh, sorry, this y is not, this is 1, my bad. So this is 1.1 into sigma c square root of pi. Let's keep the a in the millimeters for now. Or let's convert that to meters. So 0.5 into 10 to the power minus 4 meters. And all this is under the square root. So when you solve this, you will get 40 megapascals divided by 1.1 into square root of pi times 5 into 10 to the power minus 5 meters. And then you had the meter square root equal to sigma c. So finally, you will get a sigma c value in megapascals. And when you solve this, you have to see, and then you can convert this sigma c. So we know that stress equals to force upon area, where force upon pi d naught square by 4. You can calculate the force max as sigma c times pi times d naught square by 4, where d naught is the diameter. And then to tell if the part will the part fail by fracture or necking? So let's try to draw a stress strain diagram real quick. This is sigma, this is epsilon. In a stress strain diagram, generally you will have a system looking like this. So I'll just mark quickly the points. So this is the proportional limit, this is the yield strength, this is the tensile strength, and this is the rupture or the fracture. Right, and this is the elastic region. This is the elastic plus plastic region. And then this entire is the plastic region. And in this plastic region, this region is the work hardening. And then in this last region is where you have necking followed by a rupture, right? So we have been given the tensile strength of our material, which is 400, I believe, 300. So this is given to us 300 megapascals. And I have calculated my sigma c from here, right? So depending on the sigma c, you can calculate where does the sigma c lie on this plot. Is it or and with that you can decide, is it necking or will it rupture? As in, will you go all the way through and you'll rupture the material, or will you just neck it, right? This is a way to calculate that. And again, try to read more about the stress strain diagrams if you can, to get a revision of these values, and then you can understand how sigma c can relate to tensile strength. But this is how you can approach a question like this. Again, using the plane strain equation. At the top, we use the equation for stress concentration factor. So just to review, you have a maximum stress sigma m, a stress concentration factor k subscript t, the critical stress of sigma c, and then the plane strain fracture toughness as k subscript 1c. It's not I, it's 1. Always remember. And then the two different types of cracks, not types, but rather locations, crack internally and the crack on surface, have different y values and different crack length values, right? So this was some information and practice problems for fracture. Thank you.